And here's the last method, method 3. We are going to find the Taylor series of functions by using summation, multiplication, and divisions of power series. So if you can memorize the important Maclaurin series shown in the previous lecture, then this method will be relatively easy. Let's look at the first example. Let's find the Maclaurin series for the function, the hyperbolic cosine of x. By the definition, the hyperbolic of cosine of x equals e to the power of x plus e to the power of negative x, then divided by 2. And we already found the Maclaurin series for e to the power of x, so we can simply substitute them into this function. So this equals, I pull out the constant first, 1 over 2, then times e to the power of x also equals to the sum for n starting from 0 of x to the power of n divided by n factorial. Then plus e to the power of negative x. So I can replace the x by negative x from the same series. So this equals the sum for n starting from 0 of negative x to the power of n divided by n factorial. Let's combine them and rewrite it as a single summation. So this equals half times the sum for n starting from 0 of 1 over n factorial, then times x to the power of n, the second term, plus the sum for n starting from 0 of 1 over n factorial. And I'm going to rewrite the negative x to the power of n as negative 1 to the power of n times x to the power of n. Then I can factor out this term and rewrite it as a single summation. So this equals half times the sum for n starting from 0. I factor out the x to the power of n, then I'm left with 1 over n factorial plus negative 1 to the power of n divided by n factorial. For the terms in bracket, you can notice that if n is odd, then we have 1 over n factorial minus 1 over n factorial. But if n is even, then we get 1 over n factorial plus 1 over n factorial. So the only non-zero term is when n is even. And when n is even, then the terms in bracket equals to 2 over n factorial. I can cancel out the 2 with the half in front, so this also equals the sum for n starting from 0 of x to the power of 2n, so that all the exponent will be even, then divided by 2n factorial, since I replaced the n by 2n. So the denominator becomes 2n factorial. And that is the Maclaurin series for hyperbolic cosine of x. Let's look at the second example. Let's find the first 3 non-zero terms in Maclaurin series for the function e to the power of x times sine of x. Here we have a multiplication of 2 functions that we know their Maclaurin series. So we can simply multiply each term from their Maclaurin series. Here the function is e to the power of x times sine of x. We know the Maclaurin series for e to the power of x. If we write out the first few terms, we have 1 plus x divided by 1 factorial plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on. And we also know the Maclaurin series for sine of x. So we multiply this series by the series for sine of x, that is x minus x cubed divided by 3 factorial. And since we only want the first 3 non-zero terms, in the second term for sine of x, we already have x cubed, which is the 4th term in e to the power of x. So we do not need to worry about the other terms in sine of x. Now let's expand this. The first term from e to the power of x is 1, so we take 1 times the series for sine of x, that is x minus x cubed divided by 3 factorial, and plus the other terms. Then plus the second term from e to the power of x is x, and we multiply that to the series for sine of x, and we get x squared minus x to the power of 4 divided by 3 factorial, and plus the rest of the terms. And the third term from e to the power of x is x squared divided by 2 factorial. So we multiply that to the series for sine of x, and we get x cubed divided by 2 factorial, then minus x to the power of 5 divided by 2 factorial times 3 factorial, and the other terms. But since we only want the first 3 non-zero terms, we have an x to the power of 1, we have x squared, and we also have x cubed. So they are the first 3 non-zero terms. So I do not need to worry about the other terms, the x to the power of 4 and the x to the power of 5. Also, if I expand the fourth term from e to the power of x, I have x to the power of 4 divided by 3 factorial. Here the exponent is also 4, so I do not need to worry about this term. So let's rewrite the first 3 terms. The function approximately equals to x plus x squared, and for the third term, I have 1 over 2 factorial, which is 2, and minus 1 over 3 factorial, which is 1 over 6. So this equals x plus x squared plus 1 over 3 times x cubed. So when we have a function like this, it is hard to express the series as a single summation notation, but we can expand them. In this example, we show the first 3 non-zero terms. Now let's look at the last example for this lecture. Let's find the Maclaurin series for tangent of x, and we also only want the first 3 non-zero terms. So how can we express the function as a combination of functions that we know their Maclaurin series? We know that tangent of x also equals to sine of x over cosine of x. And we know the Maclaurin series for sine of x and cosine of x. The Maclaurin series for sine of x is x minus x cubed divided by 3 factorial plus x to the power of 5 divided by 5 factorial. And we only want the first 3 non-zero terms, so we do not need to worry about the other terms. Then divide this by cosine of x. We also know the Maclaurin series for cosine of x, which is 1 minus x squared divided by 2 factorial plus x to the power of 4 divided by 4 factorial. And again, we only need 3 non-zero terms. Now we need to divide the power series by another power series. We can use long division. So I rewrite the quotient into a long division. So for the first term, I need an x. Then I multiply the x to the quotient, and I get x minus x cubed divided by 2 factorial, then plus x to the power of 5 divided by 4 factorial. I can also rewrite the factorials in numbers. 3 factorial equals to 6, and 5 factorial equals to 120. 2 factorial equals to 2, and 4 factorial equals to 24. Then I subtract the 2 equations. I get x cubed divided by 3, then minus x to the power of 5 divided by 30. So my second term would be plus 1 over 3 times x cubed. Then I continue with the long division. I get x cubed divided by 3 minus x to the power of 5 divided by 2 factorial times 3, that is 6. Then I subtract the 2 equations again, and I get 2 over 15 times x to the power of 5. And I do not need to worry about the other terms because from here, I can get my third non-zero term, which is plus 2 over 15 times x to the power of 5, and so on. So let's rewrite the function tangent of x. The first three non-zero terms are x plus 1 over 3 times x cubed, then plus 2 over 15 times x to the power of 5. And that is the end of that lecture. So we learned all the methods to find the Taylor series of a function. But you may wonder, why do we need to express a function as a series? So in the next lecture, let's talk about the applications of Taylor expansions.